introduction to this. Electrical and electronic power and drive systems. Yeah. So the assessment for this is in 3 parts. First, number 1, you've got an assignment where you're going to analyse and critically evaluate methods of AC and DC motor control. I haven't given the assignment a good look over from last couple of years yet, but I'm unlikely to change it a great deal. A likely thing is to be given an application to have a look at, to analyse that application and what its needs are, motor and drive wise, and suggest and justify a solution. Alright, so that'll be what that is. And normal thing is I give about 3 weeks for that to be completed, handed in online in the normal way. Assignment 2 is an investigation and critical evaluation of further applications of power electronics. In the past I've picked a range of different things, DC converters, induction heating, to look at induction heating of bearings for fitting them on shafts and that type of thing, and how those systems work. Again, there'll be an assignment, bit of working class, bit of guidance as to where to look for information. Beyond that, I'll be research it and suggest a solution or, for a particular problem. Yep. And then the third part of the assessment is at the end of the module, you'll have a 2-hour examination that assesses your ability to analyse 3-phase power distribution systems. All right. Outline plan, and it is an outline plan, and I'll tell you why it's outline. All the other 2 years I've taught this over both semesters, shorter sessions, and that's very different to teaching it in 3-hour blocks. So I'm toying around with how I'm going to fit everything in, and my current plan is after this week to maybe split the session between a little bit of power systems analysis and some calcs, together with some work on motors and drives and bits and pieces. And then towards the end of the module, when the 2 assignments are finished, we'll do the analysis of power systems all for the whole session. Probably will, at an appropriate point, not the same time every week, we'll break away and have a coffee for 15-20 minutes and come back, okay? But other than that, we're here till 3:15. So, let's start having a look then. Power in single-phase AC circuits. If we apply a single-phase, if we put a sinusoidal voltage, lowercase v brackets t, meaning instantaneous value of a sinusoid, to a single-phase circuit, we would have a sinusoidal current flow in that, okay? And we could calculate the instantaneous voltage at any time with the formula Vm for the maximum or peak voltage multiplied by the sine of the frequency plus or minus any phase angle. And we could do the same with the current. For either of those 2 formulas, Vn or Im as the peak current or voltage respectively, omega is the angular frequency in radians per second. The other way of expressing that in terms of the frequency in hertz is that omega is 2 pi f. And that should be familiar from other studies, hopefully. Okay? And in each case, theta 1 as the angle or phase angle of the voltage in radians in this case. So if your frequency's in omega, then your angle needs to be in radians, and theta 2 is the angle of I in radians. Although generally you'd be dealing with one of those as being no phase angle, and the other one, what phase angle is it to usually the voltage. Yep. So generally if you're doing a multiplication of those two, or using both of those, one of them will be an in-phase component with no angle added or taken away from it. Alright, everyone okay with that? Right, gents, moving on from that, consequently, as power, one way of calculating power is the voltage multiplied by the current, we can calculate the instantaneous power at any moment in time by multiplying together the instantaneous voltage and the instantaneous current. Yeah. So, gents, if we want to know the instantaneous power at any moment in time, we multiply the instantaneous voltage by the instantaneous current using that formula, and we can find out what power is being drawn or used by that circuit at any moment in time. So, if we look at that, I want to talk about a term called active power, that measured in watts. If we apply an AC voltage to a load that is purely resistive, in nature, current and voltage are in phase with each other. They will be in phase with each other. No phase shift in that circuit. So in this graph here, the blue waveform is the voltage waveform. The red one is the current. Yeah, and there's no phase shift between them. So every time the blue one crosses zero, the red one is also crossing zero. When the blue peaks, the red is peaking, and so on. If we calculate the power instantaneously all the time through those two waveforms, we get 2 power pulses for every 1 cycle of the mains. Yep. The other things that you need to be aware of, so we got the power pulses are twice the frequency of the supply. The other thing you need to be aware of is, in the formulas on the previous page, Vm sine omega t, that Vm is the peak value of the voltage, peak value of current if we're talking about Im. Power is calculated from the effective or RMS values of those voltages and currents. Okay, so to get the RMS value of voltage, you take the peak value and divide by √2. It's the effective DC value, yeah. It's a value that would be I'll put it on another slide in a minute, Joe, all right? But you're correct. It's the equivalent DC value of that AC sine wave, okay? It is only √2 for a perfect sine wave. If the waveform was a different shape, it wouldn't be E peak of a √2. It would be a different formula for that, okay? and a RMS current is the peak current over root 2 as well. Okay, so if you've got an RMS value, you multiply by root 2 to find out what the peak is. So to be very careful when you're reading a question as to whether that's talking about the peak value or whether you're talking about the RMS values. And if you're given a voltage in this form, it must be talking about that being the peak. Yeah. If you're told the effective value, you're being given the RMS value. Okay? Because that's the waveform, and this is peak. RMS, if there's 0 along there, RMS is root 2 times the peak. It's a DC equivalent value and is a straight line. So when they say the mains from these sockets is 230 volts nominally, that's the RMS value. It's the value that would give the same power in the same load as the same voltage DC. Yeah. That's the yeah. Hang on. Peak over root 2. This value here is peak over root 2. It's got to be less. Yeah. When you've got a bit of -1, a bit of +1 added together to make it gives you the useful power from that system. Okay. Now, a useful practical point to this is cheaper digital meters measure average voltage and current and convert it to RMS, but that conversion process is only good for a per sine wave. So if you're using it on any other shaped waveforms, you won't be getting a true RMS reading. To do that, you need to spend about 2 or 3 times as much money on the meter to get a true RMS meter that actually measures the RMS value and not an average converted. Okay? I'm not up to date with the current costs of instruments, so I don't know what the difference in price is, but there always used to be a considerable difference. When I was in the industry, you probably had to pay £700–800 for a true RMS multimeter, good quality one. Is it not?
Yeah.
Okay. Yeah. All right. You only spend that money if you need it, really. So, moving on from that, then, we need then to talk about what we mean by something called reactive power. Yeah. There are 2 types of that. The first one is where the load is inductive, and we'll talk first about a load that's purely inductive. There is only an inductance. We assume it has 0 resistance. I've drawn 2 phasor diagrams representing that circuit. The first one is the phasor difference between the voltage of the supply and the current flowing in it. And anyone remember what the word is to help you determine? Civil, yeah. C-I-V-I-L. In an inductive circuit, so we're just looking at that half, current is after or lags the voltage. We always talk about these phasors rotating in an anti-clockwise direction, therefore the current is behind the voltage here. Or we could equally say the voltage is leading the current. So current lagging voltage or voltage leading current is correct for that circuit. Okay. We also can draw a phasor diagram representing the active power in that circuit. The reactive power for an inductive circuit, or the reactive power, uses the symbol Q, and here we're talking about Q for the inductor, so we talk about QL. What it's done is it uses power, the reactive power being used by an inductor, as the power used to magnetize or create the field in that inductor. So it's creating a field in one direction, and then passing it back, and then creating the field in the opposite direction, and then passing that back. So when you connect an inductor to this circuit, in one half cycle it's drawing power away and then putting it back, and then it's drawing power in the other direction and putting it back. Doesn't actually do any useful work in that inductor. No heat, no change to any mechanical movement at all. The reactive power does not do any useful work. Everything taken from the source is given back again. Yeah? No useful work done. And you can see from the same type of diagram, here again, the blue waveform is the voltage. The red one is the current. We multiply all the instantaneous values of those together. We get a power pulse in green that's got one half of the cycle negative, the other half positive. Therefore, in this section, if we consider there and there, we're taking power from the source. Don't really matter which one you call taking it. You could call the other one taking it. Wouldn't matter. In here, we're giving it back. And in there, we're giving it back. So no overall power in watts that's being used or converted into another form, because that's what electricity is about. We take electricity in one form, we convert it to a useful form, like a motor turning, or a heater heating up, or a light emitting coming from a light. Yeah? None of that is happening in this type of circuit. The waveform shows that for each power pulse there's one matched by a negative one. No electrical power is converted to useful power. Inductive loads are said to absorb reactive power, QL, from the source. Okay? So the general term is that they actually take a positive reactive power. Reactive power also, good point, is measured in VAR. VAR, that term is short for volt amps reactive. So it is still the product of the current and the voltage, but they are 90 degrees out of phase with any resistive current and voltage, represented by this phasor diagram here. So this sign it absorbs, or as a positive use of reactive power, means that we've got a positive phasor for it. It's pointing 90 degrees upwards. And that'll become a little bit clearer of that when we've covered the other reactive power, the capacitive reactive power, in a minute. Is everyone okay with that?
Say, for example, you're using that coil to do some mechanical work. Is that going to cause a phase shift? Say, for example, in a solenoid, would that cause a momentary phase shift?
If that coil is what we're modelling here, an absolutely pure inductor, i.e. Henry's only and no ohms, which is not achievable in real life, okay, you would get a 90 degree phase shift between voltage and current, as shown on this diagram here. They're actually, as the voltage crossing zero there, the current crosses zero 90 degrees after it. Yeah. So the current is lagging 90 degrees behind.
No, I'm sorry, I'm thinking
Yeah.
if you actually put a roof on the magnetic field.
Yeah, well, yeah, we're going to come to that a bit later, but once you add a resistor in there, I don't want to do it on this diagram, but we'll come to that later, you then don't get a perfect, you've got a 90-degree component, a 0-degree component, and you've got a resultant between the two. We ain't got that far yet. Okay? So you've got two currents out of phase with each other. Yeah? Alright? So, hang on. Couple of more bits to talk about that situation. Yeah? There's a number of ways that you could find out what the reactive power absorbed by the inductor, QL, is. You can find it from the generator voltage, in this case, the product of generator voltage and the inductor current. Yeah. You can find it from the inductor current squared multiplied by the inductive reactance, and we've got XL we can get from omega L or 2 pi FL. Yeah. And you can find it from the generator voltage squared divided by the inductive reactance of the coil. And transformer data sheets will tell you things like what the inductive reactances are and bits and pieces, and either that or things can be measured. But generally you're going to be finding it mostly from a voltage and a current. The other type of reactive power, okay, is where the load is purely capacitive. Again here, the load is purely capacitive. The current leads the voltage. So if I write the word civil up here again, but we're looking at a capacitive circuit this time, this half. In a capacitive circuit, the current is ahead of the voltage, it leads the voltage, or you could say the voltage lags the current. So in our phasor diagram here, going around that way, the current here is ahead of the voltage here. Or we can say the voltage is behind the current. When we draw the phasor diagram for QC, it is a negative phase angle of 90 degrees. We're going to be doing some calculations that will involve us using complex numbers. That would be, for QC, you'd be using a negative J term within that formula work. In terms of QC, a positive J term with the inductive side. And I have asked, after this session, there's still got the advanced math support with Mark, okay? And I have asked him today to do a little refresher on complex arithmetic. Right? Again, this reactive power QC is measured in var, short for volt amps reactives. It's got the same units as the inductive one. And overall, when we look at whole circuits, we're going to be interested in the difference between those two. So you're going to have a negative, you're going to have a positive reactive power, and if you've got capacitance as well, a negative reactive power, and the overall reactive power in that circuit is going to be the difference between the two. But more about that later, possibly next week. When we plot the waveforms for this circuit, again, we've got the current in red, the voltage in blue, okay, but this time the current is peaking ahead of the voltage by 90 degrees. Our power pulses again have got positive and negative sides to them, but they're the opposite way up to what they were with the inductor. The inductor went underneath first and over the top second. Alright, so here the capacitor is charging there and there, and here it's charging up the other way. So it charges, discharges, charges in the opposite direction, and does that twice per cycle. Overall, again, no real work is being done. Apart from charging and discharging it, there is no resistance in this theoretically capacitance only circuit, so no work can be done. No power in watts is being used. Capacitive loads are said to supply reactive power, QC, to the source. So you've got to choose a direction for each of the two different ones. So somebody's arbitrarily said inductors draw reactive power from a source, capacitors give it back. Yep. In reality, when one is drawing, the other one's passing back and vice versa, because a capacitor's got to charge up, so as an inductor's got to charge its field. But when the inductor's charging its field, the capacitor will be given some charge back again, and vice versa. Yep. If there's both in the circuit. Quite often in industrial systems, you ought to probably know that there usually is, in the form of some power factor correction capacitors. Yep. So, again, a little bit more about these phasor diagrams and how you can calculate values for QC. We can get it from the generator voltage times the capacitor current. We can get it from that current squared times the capacitive reactance XC, and we can get it from the generator voltage squared over XC. Again, XC could be calculated from 1 over omega C, or from 1 over 2 pi times the frequency in hertz times C. Always bear in mind capacitance values in that formula are in farads, even though they're likely to be values in microfarads times 10 to the minus 6. Alright. So, we need to have a clarified distinction, really. This is to clarify everything I've covered so far in a way, between active and reactive power. First of all, one cannot be converted into the other. They function completely independently of each other. You can't convert power in watts into vars or vice versa. Okay? They can be treated as separate quantities in electrical circuits. So when we're doing calculations, we deal with Q and P and another an amount called the apparent power, which we'll look at in a minute, which is the combination of the two. They're treated as separate quantities. Both of them, despite not doing any useful work, place a burden on the transmission lines that supply the equipment, because when the inductor is charging up and drawing current, that current's got to flow down the transmission line and back again, and so is the current charging and discharging the capacitor. Therefore, this reactive power is drawing current backwards and forwards despite not producing any useful heat, light or mechanical motion. Active power produces a tangible result in the form of work done. So the watts does. It produces heat, light or mechanical motion. Reactive power does no useful work. It represents energy that oscillates backwards and forwards between its magnetic field and the source in the case of an inductance, or between the charge on the capacitor and the source in terms of a capacitor. A large system such as a factory or a oil rig or wherever it is you work, quite often, invariably really, presents a large active reactive load in the form of heaters, motors. As soon as you wind a coil, you've got an inductor, even if that's just that loose coil on a 3-bar electric fire or something. You've got some inductance there that's going to cause some reactive power. They draw reactive loads, and they do that to sustain the magnetic fields. So in transformers, you've got to sustain a magnetic field. In a motor, they wouldn't work without a magnetic field. Okay, so active loads provide heat and mechanical energy. So what we need to do then is consider loads that absorb both active and reactive power combined. Yep. So ones that include both. What happens when we get both of them in a circuit? That's what we're going to do now. So if we come up with a circuit where we've got and that's what you were on about, Bob, wasn't it? When you connect a load, was it you? I've connected a load now, a resistor, across the inductor. So we've got a current flowing through the resistance, and we've got a current flowing through the inductor. Okay. In that case, we've got a combined current voltage phasor diagram. Here's E. This board is getting on my nerves. There's E, and I've just moved it down a little bit so you can see the second arrow, but that one there is representing the resistive current that is in phase with the supply voltage. Here, if we use the word civil, and we're looking at that side, the inductive current lags the voltage by 90 degrees. So this here is representing IL. Okay. The line current, that's this one here, is the resultant, or the total current in the circuit, is the resultant of those two. And as you can see, it draws that current out of phase with a supply voltage. They're not in phase with each other anymore. So we've got a current IR in phase with the source voltage, whilst IL lags it by 90 degrees. The current drawn from the source hence lags the supply voltage by an angle theta, and that angle will depend upon how big the inductive current is to the resistive current. If we make the inductive current bigger, it's going to pull the angle down and make the current drawn from the supply bigger and the line longer. If we make the reactive current smaller, it's going to make the angle smaller. Right? The phase angle between the two. The waveform now shows two positive areas representing the real power in watts. So these two above the line in blue there represents P in watts. These two small bits down the bottom here, there and there, their size again will depend upon the relationship between how much in phase current and how much out of phase current we've got, i.e. the difference between the reactive and the active currents. But those two red bits down there are the Q measured in var. So this bit is using useful power. That's the inductor giving back power to the source. Reactive power to the source. So these are active, they're reactive. It's all right, Alan, no problem.
Yeah, sorry, mate.
Looking a little bit deeper at the combined situation, the magnitude of the current drawn from the source from this phasor diagram can be determined using Pythagoras theorem. So we've got a triangle situation here where we've got an in phase current IR, we've got an out of phase 90 degrees out of phase current IQ, and we've got a line current IL that is the hypotenuse of a right angle triangle. It's quite easy if we know any two of them to use Pythagoras theorem. A line current I is a square root of IR squared plus the square root of IL squared. So all that trigonometry you done at school and everything is useful in electrical. It is in mechanical as well for forces, isn't it? So the magnitude of the angle, theta, depends on the value of the inductor and the value of the resistor as well, really, because that's going to affect the in-phase current. Consequently, the larger this angle is, the greater the current required to produce a given amount of power. Yeah. So for a given resistance there, that's going to give us a given amount of power. If we get a much higher inductance level, a much higher reactive power being drawn from the source, that phase angle is going to be wider, and therefore if we make this phase angle here a wider one, up there somewhere, the length of that IL line becomes longer. It's drawing more current from the source for the same amount of resistive current, and therefore the same amount of power. The voltage doesn't change. Yeah. So we still get the same amount of real power dissipated, the same amount of heat out of it. It's going to cost us more in current, which has implications, and we're going to have more about that shortly. Yeah, it's cost implications, certainly does. All right. Any questions? So, we've looked at real power, we've looked at apparent reactive power. Well, now we need to consider what is the resultant of those two, the apparent power in the circuit. Uses the symbol S, and some of you might have noticed that transformers are rated not in watts, but in VA, volt amperes, or kVA. Or if they're really big ones, MVA. It is the product of the line current and the line voltage, volt amperes. So the combination of real and apparent power produce a resultant. So here's our apparent Q here, is our reactive power. P is our real power in watts. We get a resultant between those, S, in volt amps, and there's a phase angle between them. So we can calculate S by multiplying the line voltage by a line current, or from the power triangle, square root of the power squared plus the reactive power squared. The apparent power forms an angle with the real power, theta, that is the same as the angle of the lagging current produced by this circuit discussed earlier. Alright, so you can get the phase angle and effectively the power factor we're going to talk about shortly from either the relationship between the angle between P and S, or from the angle between the currents, the actual line current and the current due to the power. That angle works out to be the same from either triangle. Alright, any questions on that? So, reactive loads and power factor. Many reactive loads on a system that require reactive power Q to set up the magnetic fields. They include motors, transformers, heaters, welding plant, X-ray machines, dozens of things in a factory industrial situation taking reactive power. If we have a high reactive load, the left-hand diagram, Q is relative to P is quite large. It means the supply lines have to carry more current, because if we assume voltage stays the same, then if that line is longer, the current must be more, okay, at a given voltage to provide the same amount of power. So if in those two diagrams we assume that the power line is the same length, the left-hand one draws more current from the source than the right-hand one does, because the angle is less, the reactive power is less, and hence there's less current being drawn to create that VA line the same length across the top there. So a lower reactive load means less current is carried in the supply line to deliver the same amount of usable power in watts. The S line of the triangle is shorter. Alright? Yep. Which leads us on to what we mean by power factor. That left-hand triangle is termed a circuit that's got a low power factor, the right-hand one, high power factor. Power factor for a particular load or combination of loads, in a week or two, we're going to look at how we can actually do calculations using PS and Q on a number of loads that might be connected to one generator all in one go, and just by separately considering all the power bits, all the QL bits and all the QC bits added together to do a combination calculation on a load center, if you like. Okay, so power factor is the ratio between the real power in watts and the apparent power in VA. It is the cosine of the angle theta. And if you look on some big distribution centers, they'll have a meter telling you what the cos theta is or what the power factor is. And if a power factor of unity or 1 is an angle of 0, so it's a perfect non-reactive load. Generally don't get to that in an industrial situation, because once you get beyond a certain point, you don't get the payback on the amount of capacitance you have to add to get rid of any more reactive load. So our power factor is the cosine of this angle, or we can get it from the ratio between S and P. I've recovered that now. So just moving on, implications of poor or low power factor. We already discussed these two triangles and that we get more current, need more current where we got a low power factor than where we got a high power factor. A transmission line, like the national grid for instance, can only carry a finite amount of current for a given cable size and pylon size and everything. Because a low power factor results in more current being needed to produce a given amount of real power in watts, okay, less useful energy can therefore only be transmitted on that line if you've got poor power factor. For that very reason, that leads to supply companies penalising the ones that own or supply the transmission lines, that penalise larger consumers for poor power factor. And they do that through the tariff. What they do is they base, or they make a charge, a monthly charge, dependent upon your maximum demand in kilovolt amps. So if I remember back, I used to check this when I worked at Fibronal, and they'd record what the maximum demand was each week, and they'd keep an eye on it. That was a meter that had a needle on it in them days. You know, the types of things where I'll push a maximum marker up beyond where it was before, so when it falls back, probably electronic now, but they'd have a meter that indicated in that month what your maximum demand was. And I think you used to take a reading of demand every so often or something like that, and then record what the highest was. And they'll then make a monthly charge based on that highest demand. And I had a little search on the internet, and I got a table for electricity company on the island of Jersey of all places. But on a low volt, just as an example, on a low voltage 230 400 volt, and make a maximum demand charge of 820 pence per kV kilovolt ampere of maximum demand. Yeah. So that's 8 quid per kVA of maximum demand. So you've got a maximum demand of 100 kVA. That's 800 quid a month they're charging you on that maximum demand. If you're a high voltage user of electricity, if you were to take your electricity at 11 kV, the cost for maximum demand is slightly less. But then they're going to be getting more out of them anyway, because likely their load is significantly higher. The implications here are is you don't really want lots of motors all turning on at once, because that could potentially stick your maximum demand up. Either that, or you want some local power factor correction to make sure that they don't do that in the first place. So there's two ways of doing. We haven't discussed power factor correction yet. There's two ways of doing it. One is to have it overall on the load center where your switchboard is. The other is to have it locally, power factor correction mounted actually on at the local point where the motor is, and sometimes both. Usually the load center stuff is automatic, so it'll switch in and out according to the changes in reactive load. But we're going to discuss power factor correction possibly next week or the week after. Alright? But what I'm trying to give here as an indication, and there's a question in the tutorial questions that looks at the difference in that cost if you improve the power factor by a certain amount. It's quite significant and important for people that are paying for the electricity. So before I give you the tutorial questions, I'll just put a quick example up on the board so we can run through one and just clarify where the results might or could come from. So I'll give you a couple of minutes to write that down. A 400 volt motor rated at 4 kilowatts draws a line current of 15.6 amps. Find the apparent power S, the reactive power Q, and the power factor. I'd like to find that. Right, gents, so how can we go about doing that? A, how can we go about finding apparent power? Yeah, that's VL, the line voltage which you've been given, times the line current, the current that's drawing, because you're measuring that with an ammeter, for instance. So simply the 15.6 amps multiplied by the 400 volts. Someone will push some buttons for us, I suppose. 6240 volt amperes. Yeah. And up here, what I'm going to start to do, I do recommend that you do this in these types of questions, is build your right angle triangle so you can see where everything goes. We now calculated S. I'm going to put the calculated values in red. That's 6240 VA. Yeah. Reactive power Q. How can we calculate that? In this instance, Pythagoras theorem. So that's going to be the theorem actually rearranged a little bit. It's going to be the hypotenuse squared, take away the power side of it squared. So that's the root of 6240 squared minus 4000 squared. Again, expect someone will push some buttons for us. 4789 units. Daniel, oh god, that's all right. VAR, yeah. Four, 7, 8, 9. It stands for, it is volt amps, but the R is representing volt amps reactive. Okay. On real power system, we're quite often here going to be talking about kVA, kVAR, and kilowatts. And if you've got all of those three quantities in K, you can just put the numbers in and the answers in K. So if you've got the power in kilowatts and S in kVA, you can just put the numbers in and you'll come out with Q in kVars. Yeah? C, the power factor. How are we going to calculate that? Yeah, it's P over S, because it's the cosine of the angle. Yeah, cosine is adjacent of a hypotenuse. That's the 4000 over the 6240, which is that's a ratio, so I ain't got any units. 0.641. Not untypical for a power factor of a motor. 0.6 could be 0.4 and 0.7. Yeah, so that's not untypical at all. All right. I'm going to